So can I start now?
Yeah, please.
Yeah. So next speaker is Professor Seung-hyun Kim, Gyeongnam University. So Professor Kim is currently professor at the Civil Engineering Department of the Gyeongnam University in Republic of Korea. His research interest includes innovative membrane-based seawater desalination technologies such as MD and pressure-retarded osmosis. Based on his expertise, he successfully led the research team called GMBP, who worked to develop the scaling up technology of MD, PRO, and resource recovery of lithium, and various forms of their hybrids with RO for last 5 years. Also, Professor Kim is the very historic the desalination experience. He is one of the longest research contribution for seawater desalination in Korea, more than 20 years. So even though a lot of people do not know about who is the Professor Kim, but in fact he's the most contributed in desalination in Korea. So please join me welcoming Professor Seung-hyun Kim's presentation. Professor Kim, so you can share your slide.
Can you see my the presentation file?
Yes, I can see you.
Okay, thank you for your introduction. My topic today is about a pilot scale evaluation of membrane distillation and pressure-retarded osmosis for seawater application. As Professor Sean mentioned, I have been involved in a research to study scaling up of these membrane distillation and pressure-retarded osmosis. So I'm going to share these experiences at this presentation. Down here, you see, you find many names. They are the people who actually contribute to this work, but I'm not going to go through these names by name because of time frame. Okay, this is a seawater desalination in Chinese characters. Because this is a membrane desalination, I'll start this presentation by showing seawater desalination in Chinese characters. There are 5 characters. These first two characters are seawater, and next two are freshwater, and the last one is to make. And Chinese characters, they have a meaning, and you find the common character, second and fourth one, these are water. And if you just move to first one, Chinese character, they often consist of several components. And this one, this can be break down 3 different components. And this one, the left one, is another expression of water. And down below, the right one, this one is mother, which means sea is mother of water. So when ancient Oriental people, then they look at sea, they imagine a mother. Probably that's the reason why they came up with this combination to express sea. And then move to this fresh water, 2 components. This is water, and this is fire. But you have 2 fires. Probably they understood when they add lots of fires, they could produce fresh water. That's the reason they made this combination. So that is exactly thermal desalination. So thermal desalination has been known very, very long time and has been very popular to dissolve seawater. And it actually dominated the seawater desalination market at least until last millennium. But now things different. Now it's a membrane time. Membrane desalination dominates the market. So I'm going to talk about this membrane desalination in this presentation. With some background, I'll talk about MD scaling up. This is the main portion of this presentation. Then I move to Pro, scale up. I briefly mentioned scaling up. Then, with some thoughts on scaling up, I'll conclude the presentation. Why we choose membrane distillation and pressure retarded osmosis? It's because this one is good for brine treatment. And this one shows the primary process of seawater desalination. Seawater desalination, it produces fresh water, but it also produces concentrate. We call it a brine because of its high salinity level. And this brine discharges back to the ocean. And there are some concerns of this brine discharge impact on marine environment. So how we solve this problem? There are two possible ways to minimize or solve this problem. One is dilution approach. The other one is zero liquid discharge. Here, this schematic shows these two different approaches. You take out the brine and dilute using the impaired fresh water like a secondary effluent, treated secondary effluent. And if you just apply here PRO, you can harvest salinity gradient energy because there exists salinity gradient between seawater brine, desalination brine, and impaired fresh water. That way you can recover extra investment. And down here, you squeeze further RO brine and produce distillate and more concentrated MD brine. It's very good for resource recovery. So these two, when you look at these two alternatives, you can find the two key technologies is membrane distillation and pressure retarded osmosis. That's the reason we started studying these technologies, because seawater membrane desalination is a kind of major technology. So we see the future of seawater desalination and brine treatment, and the key technology is membrane distillation and PRO, pressure retarded osmosis. So we conducted scaling of study of these technologies over two projects. First project, we call that research team GMVP, funded by Ministry of Land Infrastructure and Transportation, KAIA. It's a 5-year project. It started 2013, ended 2018. The main mission of this project, design and fabricate a pilot. We design and fabricate a membrane distillation pilot and probe pilot and lithium recovery pilot. Then a second project just started just after first project. We call this research team MD Plus, funded by Ministry of Environment and KT. This is a 4 years project. This one is still ongoing. It's going to complete next June. This one is more focused on membrane distillation, especially operation. So this project require to demonstrate continuous operation of this MD pilot plant for at least 6 months. And there are some requirements of this pilot plant, like a PR or performance ratio and specific energy consumption. Okay, membrane distillation is a thermal process driven by vapor pressure difference using membrane. So compared to membrane process, this one is, you expect less fouling. Probably that's the reason this one is, we apply this one to treat concentrated feed waters like a brine. But downside of this technology is thermal energy requirement. Thermal energy is required to create the vapor pressure difference. Because this one is driven by the vapor pressure difference, we need to provide the vapor pressure difference across hydrophobic membrane. We usually do that by temperature difference. So thermal energy is usually required. And this technology has not yet commercialized. So we have very little information available on scale up of this technology. And we don't have experience on long-term operation of this MD pilot plant or just full plant. So what is scaling up? If you just look at the dictionary definition of scale up is to increase something in size, amount, and production, or increase according to a fixed ratio. But it turns out scaling up is just more than size increase. That's what we learned from this study. I'll show you one example. This is a graph. This graph compares performance of a lab scale module and full scale module. Even though we started with same fibers, when you manufacture lab scale and full scale module, there's a big difference in their performances. So scale up is more than just size increases. And this slide, it shows procedures of scaling up. And this is membrane process. We use membrane for this technology. So we first develop the membrane, and then module. And with this full-scale module, we design and fabricate a pilot plant. And with this pilot plant, we operate it. So I'm going to talk about this scaling up results and these orders. Okay, first you have to decide whether you go with the flat sheet or hollow fibers. You all just membrane experts, so I'm not going to go through pros and cons and flat sheet and hollow fiber. We decide to go with the hollow fiber because of this high packing density. And this slide, it shows 4 hydrophobic polymers, their properties, hydrophobicity by contact angle, thermal conductivity, raw material cost, membrane cost, mass production easiness, and oxidant resistance. Actually, you can choose any polymers, but we choose a polyethylene and PVDF. This one is related to the manufacturer. The manufacturer to work with us at the phase 1 project is Equinity. This Equinity, they are specialized in polyethylene fiber fabrication. So we selected polyethylene and PVDF. And this slide, it shows effects of membrane properties and mass heat transfer. Pore size, larger the better in terms of mass transfer, but it decreases liquid entry pressure, then membrane becomes wet. And porosity, higher the better for mass transfer, but in terms of production, this pore size and porosity, they are related. So you have to set on certain values. Tortuosity, straighter is good for mass transfer, and wall thickness, thinner the better for mass transfer, but thin membrane, you lose heat very quickly. So you need to provide certain thickness. Thermal conductivity, it is decided by when you choose polymers. So we developed the fibers for membrane distillation application. And this slide, it shows properties and PE and PVDF fibers. Both fibers, they have a very similar properties, pore size, porosity, and contact angle. The only difference in thickness, PVDF fiber, it has a thicker, it is thicker than polyethylene fibers. And we also developed a full commercial module for MD application. Actually developed 2 modules. One is a VMD, vacuum membrane distillation configuration. The other one is we can use for VMD and DCMD, direct contact membrane distillation. And this slide, it shows a VMD module. And this one is material is ABS. A potting material is polyurethane, heat-resistant polyurethane. It is 1.2 meter long diameter and 260 millimeter. Fiber length is 450 millimeter. The membrane area inside module is 10 meters square. The filtration mode inside out is the maximum temperature is 80 degrees Celsius. And we check the module performance using the synthetic seawater, groundwater sparked by the salt, to mimic the brines, arrow brines. And we operate this one at 75-degree vacuum pressure, about 0.15 bar. And this figure shows the results. You can see here the production capacity is just below 4 tons per day. This one is for 2 modules. For each module, production is about 1.8 cubic meter per day. So with these full commercial modules, we developed a VMD pilot plants. Actually, we developed fabricate 3 plants. Plant number one is capacity is 400 ton per day. It's big one. We fabricate this one at the project phase 1 GMVP, and pilot plant number 2 and number 3 is smaller one, and this one is fabricated at the project number 2 phase 2 project MD plus. This one is mainly for operational technology, long and secured operation technology, and the other one is going to use for continuous operations. When we fabricate this pilot plant, we have a 2 possibility. Is it possible we can build a pilot actually producing steam? That was one question. And number 2 is sustainability. Is it going to be sustainable? Is it going to be sustainable in operation for a certain period? About fouling control, about wetting, is fibers fouled, or these kind of things we had in mind before we started fabricating these pilot plants. And this pilot plant, we installed the energy recovery devices. This is a thermal vapor recompressor. Now, this is a thermal vapor recompressor. This one supplies heat energy to operate this MD operations. And this thermal vapor compressor, they have 2 heat sources. One is motive steam, the other one is suction steam. This suction steam comes from membrane distillation. So membrane distillation, you produce steam, and part of steam sent to the TVC, so that we can save the steam to operate these MD operations. And this one shows the picture of a VMD pilot plant number 1. This one is coupled with the RO plant. This RO plant capacity is 1,000 tons per day. Its brine is fed to this VMD pilot plant number 1. Actually, this one has 2 units. Unit number 1 and unit number 2, they have the same capacity, 200 tons per day, but slightly different module arrangement. First, unit number 1 have 120 modules, and unit number 2 is 104 modules. And we built a second pilot. This one shows the fabrication and transportation. After fabrication is sent to the site, southern port of Korea. It was transported to 2019, and after utility connection and a permit and a site preparation, it's been in operation since 2020, last year. So I'm going to share these operational results. We also fabricated a pilot plant number 3. This one shows the picture of this pilot plant fabrication. This one is a 3D drawing. And this one is going to be used for the continuous operation, not in Korea, in Saudi Arabia. So we're going to send this pilot plant in Saudi Arabia. It's going to be operate there for 6 months. So we installed extra CCTV and infrared cameras just in case to detect heat leaks. And we can monitor, and we can actually operate this pilot plant in Korea. I'm going to share some operational results. And this slide shows a flow chart of this VMD pilot plant. Originally, this pilot plant has a pre-treatment of sand filter, but sand filter was not enough for particle removal. So we reinforced pre-treatment with microfiltration, and then pre-treat seawater sent to BMD pilot plant. This one is the BMD pilot plant #1 model. We just make this one using the 3D printers, and we use boilers to produce steam. We couldn't find the waste steam, so we just installed the boilers, and boiler provide the steam required for this MD operation. We made a short video introducing this pilot plant. This is the YouTube link. You can go into this YouTube to find out more information about this pilot plant. And this one shows results, the production and PR. This blue line is production. This orange line is PR. We tested different operational conditions, also different modules, also different number of modules, so that production was different. Its capacity is 4 tons per day, but sometimes, because of different operating conditions, sometimes higher than 4 tons per day, sometimes less than 4 tons per day. PR is just usually just above 1. And this slide shows water quality analysis data. This seawater, you can notice high suspended solid concentration in seawater. Suspended solid concentration is 34 milligram per liter, and turbidity level is 21 NTU. And after sand filter, still very high in suspended solids and turbidity level. So lots of particles actually sent to the membrane distillation module. It creates a problem, a fouling problem, actually pore blocking problems. So we installed microfilters, and microfiltration is successfully reduced the TSS level 1, so that we can operate in better conditions. And this column shows MD permeate ionic concentration level. You can see here, level is very low, so that ionic removal is more than 4 low removal. And we actually concentrate MD feed by increasing recovery to see how high concentration this pilot plant can handle. We increased MD feed TDS level up to about 1,100 milligram per liter, and we didn't see any problems. And this slide shows the comparison between design and operation of this pilot plant #2. When we design, a vacuum pressure is 0.15 bar, and temperature is 75 degrees Celsius. Circulation flow rate is 4.2 meter cube per hour. We expected the production is 4.2 meter cube per day. PR is 1.75, and SAC about 2.1 kilowatt hour per meter cube. Actual operation, similar condition, only difference in circulation flow rate, 3.4. We have a higher production, but flux, you can notice flux is lower. Is it because the module number was different? Here, design is 2 module. This operation, actually, we got this result with 3 modules, so the flux was a little lower. The PR was also lower. This one is related to the TVC, the suction steams. The suction steam is actually, at the design stage, we designed about 50% steam is 50% suction steam and 50% motive steam, but actual suction steam amount is about 20 or something, 20 or 30%. So because of that, we have a low PR. Energy consumption is 2.1, but this one is based on the pump efficiency is 64% and 78% pump. Vacuum pump is 78% and circulation pump is 64%. So that if you have the pump with higher efficiency, you can actually lower these SACs. We did some autopsies. 3 autopsies actually with the VMD pilot plant. This one is polyethylene fibers, inside-out filtration mode. We did autopsy because of pore blocking and potting brackets. We also did autopsy for DCMD pilot plant. And this one is not in this project, but we also in a different project, we built a DCMD pilot plant. This one fiber PVDF. This one is outside infiltration mode. This one is used 5-month operation. We took it out after 5-month operation and did the autopsy. Pore blocking is, this one shows a production and pressures. You can see here, production with operation, production decreased and pressure increased. So we took out the module and examined the module inlet and outlet side. You can see here, this outlet side, you can see some holes. But this inlet side, these holes are blocked of this, because of this suspended particles sent into the module. And when we did the elemental analysis of these suspended particles, they are aluminum silicate, some ions, but they also contain aluminum and silicate, which means they are suspended particles. So we installed microfiltration to solve these problems. And sometimes we have a potting brackage problems. Some modules, they have a damage, a defect in potting. So you can see here in this picture, the salt outside these fibers, even though this one is inside out filtration mode. But still, this membrane, when we took out the autopsy test, we find some coatings, foulness inside the membrane. This one it was found at calciums. When we did the FTIR and XLD analysis, we found out this foulness in mostly calcium carbonate, some sulfate, calcium carbonate, and the sodium chloride. And we also checked the tensile strength and wettings, and tensile strength was fine. Wetting, the fibers were not wetted. And DCMD operations, this one is small plant, about 100 liters per day. The brine electric conductivity is about 90 millisiemens per centimeter. This one is sent to the actual desalination plant, fed to the brines, two different brines, RO brine and MED brines. Initially, it started the operation with RO brines, but after 2 months, the feed was switched to the MED brines. And this one shows the temperature, and this one is DCMD, and temperature is about, feed temperature is about 60 degrees. And this one is fluxes, and flux is stable, about 2 LMH with RO feed. But after we switch to MED brine, this flux declined. And this one, this right-hand side graph, it shows electric conductivity. And when we switch to MED brine, the permeate conductivity also increased. So we took it out and did some autopsies. And this slide shows the DCMD autopsy results. Fouling, we cut the foulness, measure their constituents, organic constituent and inorganic constituents. These are the results. We find some ions and TOC levels. And this one shows the SEM pictures. And this is elemental analysis. And mostly just the foulness with calcium carbonate. And we also did the wetting test using LEP, liquid entry pressure, and contact angle. You can see here, compare the virgin membrane, foul membrane, LEP, and contact angle decreased significantly, which indicate these fibers are wetted. So, short summary of the operation so far: fouling occurred, foulness were mostly calcium carbonate, and a particle reduction is very important for inside-out mode operation. This is ongoing study. Cleaning study is underway. we actually we are trying citric acid, sodium hydroxide, sodium hypochlorite, air bag washing, and long-term operation will soon start at Saudi Arabia with a pilot plant number 3. And we're going to organize a workshop, membrane distillation workshop, next February. We'll have it will be 2-day workshop. We'll talk about this scaling up of this membrane distillation. We're going to open this pilot plant number 2 through these workshops. If you're interested, send me email. Okay, briefly about PRO. PRO is probably very much familiar with the PRO. Its flow direction is same as FO, but the only difference with FO is you apply the pressures in the draw side. And PRO, even though this concept was known early 50s, it didn't receive much attention from researchers until 2009. 2009, Statkraft, Norwegian energy company, they built first a PRO pilot plant. And after that, 2011, Japan, they started this SWRO-PRO pilot plant study through this megaton project. And 2013, in Korea, they started this SWRO-PRO pilot plant study through this GMVP project. And this slide, it compares these three projects. Salinity gradient sources, Statkraft, they use seawater as a draw solution, river water as feed solution, megaton and GMVP. They use SWRO brine as a draw solution and treated secondary effluent as feed solution. And difference between, so that a megaton and GMVP, they have a higher salinity gradient compared to a Statkraft. And the difference between megaton and GMVP is their module. The megaton, they use hollow fiber module. A GMVP, they use spiral wound modules. And just like membrane distillation, we have the membrane manufacturers. They work together with us to develop the modules and membranes, fiber membranes and modules. They are, the company name is Dore. Initially, it was Korean company, but during the project, it was sold to the Dore. So now it's Dore company. Initially, the module they developed, their performance was not quite high. Their power density is about 1 watt per meter square. But when they gradually improve the performance of the module, and the final stage, the module performance power density was 7.3 watt per meter square. Coupon has higher power density, 18.3 watt per meter square. And we built the 2 pilots, small pilot and the larger pilot. This one is 240 ton per day. This one is about 20 ton per day. And the difference between these 2 pilot plant is energy recovery device. This one we installed a turbine. This one is just pressure exchangers. So that this turbine, from this turbine, we can generate electricity. And this one, pressure exchanger just embedded into the system. So this one is used to reduce energy consumption. And this one actually show the picture of SWRO-PRO pilot plant. You can find here Professor Wang Rong here. This is 8 SWRO draw solution, SWRO brine. A feed solution is MBL effluent. We use 8-inch spiral wound membrane module. This one is 2 p-axis, but we also installed a Pelton Hill. This one is just for extra purpose. And this slide, it shows the operational results. It's already our PRO, pilot plant. You can find here SAC. SAC is without PRO, it's mostly is 4 kilowatt hour per meter cube. But with PRO, the energy SAC was reduced to 3 kilowatt hour per meter cube. So we able to reduce energy consumption by 25%. And a lesson we learned from the scaling up and membrane distillation and probe. Module is very, very important for scaling up. So if you're just interested in scaling up study, I recommend that you work together with membrane manufacturers. A membrane manufacturer interested in developing you study, so that you can work together and with the improved module, you can actually conduct these pilot plant scaling studies. So module is very important. And for this membrane distillation and probe, right now is RO is very competitive process. You cannot find out, actually, it cannot compete against this RO as a primary process. So that's the reason probably we find the application area brine treatment, and I think we need to find another niche application areas because to develop these technologies. Okay. And I'm going to end this presentation with Chinese characters and seawater desalination again. You can see here, I just changed this freshwater. Existing freshwater Chinese character, they use fires, but I put here membrane because now is membrane time. So I think now we need to change the Chinese characters. Instead of fire, just membrane. With that, I conclude this presentation. Thank you for your attention. This is the funding source, Ministry of Environment and Ministry of Land Infrastructure and Transportation. Thank you.
Thank you, Professor Kim.
Thank you for your attention.
Thank you. Very interesting talk, and then a lot of large scale and then application oriented project. So Professor Rongwang is membrane, you are module, and if you combine, it will be a fantastic collaboration together. Yep. So we have several questions. So first question is very interesting. So he's talking about what's the leaking problem. If there is a leaking in your membrane fiber, do you exchange the membrane and then fibers or clean them for the refunctionalization? So when you have a wetting problem in your system, so how you resolve the wetting issue in the pilot scale?
Actually, leaking is potting leaking. It's not fibers. So that in that case, we just send it to the manufacturer and we reinforce the potting. Fiber is intact. So fiber is okay. And the wetting, we don't have a solution. I hope someone has a solution so that we can de-wet and reuse it to the pilot plant. So far, I don't have a solution.
So
hopefully somebody tell me the solution.
So de-wetting, if you have a wetting, so you have to remove all the module, right? So you have to change a new one.
Replace the new module.
All right.
Replace the new module.
Okay. So we have to look at the cost impact for the replacement of new module. Also, one person talking about similar to wetting issue, he's talking about ceramic membrane could have the breakthrough in MD because PVDF, P, maybe polymer could have a more wetting. How about the ceramic membrane?
I was interested in using ceramic membrane. I talked to some manufacturer when I was in Singapore. Professor Wang Rong invited me to Singapore to give a talk. After talk, someone approached me. He's a ceramic membrane manufacturer, but he didn't contact me since then. So yeah, I'm very much interested in trying ceramic membrane, but yeah, I couldn't find that because this is pilot plant. You need a full-scale module. It's not just lab-scale module. So you need a full-scale module. But I couldn't find the ceramic membrane manufacturer who interested in this study.
All right. Also, Professor Alicia An asked you a question about, do you think ROMD can achieve near zero liquid discharge in your pilot demonstration? So in your opinion, what will be the MD research impact or advantage that will bring to our environment in near future or long term?
The membrane distillation, the downside of membrane distillation is thermal energies. If you just combine with the RO brine, I did research because my research started from seawater desalination. I combined with RO brine because that is the only area we can apply this membrane distillation. But you cannot go zero liquid discharge, probably near zero liquid discharge. But then from this concentrate, you recover valuable resources, probably magnesium and boron and this kind of materials. But zero liquid discharge, I don't think so. It's, you have to go one step further. It's more like a pre-treatment. And this membrane distillation, but it's a very interesting technology. But you can actually provide the vapor pressure difference not using temperature difference. If you just provide the concentration difference, you can also have a vapor pressure difference. In this concentration difference, you don't need to provide thermal energies. So without energy, you can actually have this vapor transport. That one is a dehumidification or just concentration of food product, these kind of things. So that's the reason I talk about finding niche areas. But for seawater desalination, yeah, it's a near zero liquid discharge, and you have to add one step further, probably distillation.
All right, thank you. Also, one more question for the membrane. So is there a upper bound for MD performance? Any suggestion to improve the permeability or reduce the energy consumption of MD?
Fiber is important, but module is more important. That's what I realized. If you just work on in the lab, fiber is the most important one. But if you just work on actual field, module is more important. So I prefer if I put more emphasis on module development. Module should be the very similar, show the similar performance to the fibers, and we need to develop that kind of module. But I couldn't find the module manufacturers when I started this study. Still very interested in someone have a good idea of these modules, then we can improve these performances. But I think because actually we manufacture the modules with a higher membrane area. We used a 10-meter scale the modules, but we developed the 20 meter scale modules. But the performance was same, which means flux was half of the 10-meter scale. So we gave up to increase the packing density. So that module is more important for pilot scale study.
All right, so we have 2 more questions. So we will finish after this 2 more questions. So did you consider anti-scalant or adjusting temperature to reduce scale formation and fouling? From Michael Duke.
Yeah. Well, actually, this pilot plant study I show you, I didn't add an anti-scalant. This one is because I like to see some anti-scalants. That's the reason I did not add anti-scalant. But the pilot, another pilot sending to the Saudi Arabia for 6-month operation, definitely I need to add anti-scalant. Without anti-scalant, even 3 or 4 days operation, you see the following scales formations. So, yeah.
All right. So significant water flux performance reduction was found between lab scale and full scale. You have mentioned about module problem. Is there any factors that we need to consider in developing new membrane? Do you have any suggestion? Because it looks like a lot of membrane developed in this room. So do you have any? You are talking about module. How about membrane?
Fibers. I like to have a long fibers, and high flux in and lower heat losses. That is the key point of membrane distillation. Our fiber is 45 centimeter long. I like to go for longer fibers, but because of temperature drop, I couldn't go that far. So if you develop the fibers, have a maintaining high performance with losing low heat, then it's good. I think that is the first step direction to go.
All right. So last question. What do you think about RED?
RED is I think it's very important, interesting technology. It's going to be very competitive against PRO, but PRO we have a pilot scale test, but RED I didn't see the pilot scale test. So probably PRO is about one step ahead in piloting commercialization, but I think both one has a potential. Yeah.
All right. Thank you very much for the wonderful presentation and that answer. So please join me thanking the Professor Seung-Hyun Kim. Thank you.
Thank you.
Thank you, Professor Kim.
Thank you
for your nice talk.
He's organizing MD workshop next year, February. So if you are interested, you can join his conference and then we can have a more discussion. So today's session is end. And thank you for your participation. Tomorrow we start 8:30 in China time. Professor Manny Malay, he will talk about the ion selective membrane, which is the very important topic. So please join the tomorrow 8:30 in this session again. Thank you very much, and then see you tomorrow.